Thanks, and welcome. Thanks for coming to my talk. First, I want to start out, I work for Kitware, and we're a small open source software company known for things like CMake, the visualization toolkit, which I'll be talking about, the Insight toolkit, which is kind of a medical image analysis counterpart to VTK, and ParaView, which I'll also be talking about, Slicer, and many other tools. We're about 108 employees, most of whom are in Clifton Park, New York. I'm from the Carborough, North Carolina office, and there's a small office in Santa Fe and in Lyon, France. So we offer software support services in a variety of areas, including high-performance computing and visualization, where I do most of my work, medical computing, computer vision, and data and analytics. All right, so to give you an overview of my talk, I'm going to be spending the whole time talking about Python and its relationship with the visualization toolkit. I'm going to give a quick intro to the data model and kind of algorithmic structure in VTK. We'll talk about the Python language bindings available for VTK, some Numpy integration, and how you might create new VTK filters in pure Python. And I'll switch over to talk about ParaView, which is built on VTK and offers a lot of integration with Python. From Python, there's a Python console in ParaView. There's ways to trace your actions in ParaView to a Python script that you can replay later. There's a simplified Python interface to actually change the state within ParaView, the state of your visualization, what data is loaded, et cetera. Talk a little bit how to create Python-based filters. So in case there's not a filter available in ParaView or VTK, you can write your own in Python. And I'll touch briefly on ParaView Web. So the visualization toolkit is a little bit of an old dog, and so most of my talk will be about teaching it new tricks with Python. It started back in 1994 as an accompaniment to a textbook on object-oriented library for visualization, and VTK very much follows object-oriented approach to things. And it's still around today. It's a C++ class library for interactive data visualization in 3D. It's mostly based on OpenGL, and right now there's an effort to update the OpenGL backends to make use of shaders and some of the new technologies, and we're getting lots of rendering speed improvements with that. It features lots of ways to import your data through file readers and to export it through various writers. There are a lot of geometry processing algorithms involved, such as cutting planes, clipping, isocontour generation in 2D and 3D, and of course, rendering, 3D interactive rendering. So I was doing some research in the Git log for this talk, and it turns out I was surprised to learn that the initial Python binding support was available way back in 1997. So only a few years after VTK got started, we start to have support for Python. And today, Python is very much integrated into the VTK testing development. So there are actually 544 out of about 2,000 tests that are written in Python and get executed every time someone has a merge request. So to get you started, just a quick survey. How many of you have used VTK or ParaView? Okay. So for those who haven't, I'll give a quick overview of the real basic concepts you need to know about the VTK. And this includes the data model and what we call pipelines. So there are support for numerous data set types in VTK, including graphs and trees, grids, meshes, adaptive mesh refinement data sets. And the ones I'll be talking about today are mostly about the spatially embedded data sets. But some of what I talk about also applies to trees and graphs and such. So with the spatially embedded data set, you typically have some 3D space, maybe 2D space, that's partitioned into cells, and the cells are defined by points. Within the VTK data model, the data associated with those cells or those points are stored in arrays. And these arrays might have, for each point, they might have more than one component. Say like a vector field might have an X, Y, Z component. And so we call one of those a tuple. And there's a tuple in each data array associated with a point for point data, or one associated with each cell in the case of cell data. It really depends on what your simulation produces. The other big concept in VTK is the concept of pipelines. So VTK follows a data flow paradigm where on the right you see a graph depicted where you have something like a reader that ingests the data and then perhaps one or more filtering steps. And you could either save that out to a file or you could send it to the rendering infrastructure. And that's what the mapper and the actor and the renderer are. And it's a pipeline that you create and isn't executed until some downstream consumer requests that the upstream filters update their data. So anytime the filter changes, then each time the update request is issued downstream, then only the filters that have been modified and below that get updated. So we're going to jump to some code right now, and this is using the Python bindings in VTK. It's a simple example where I'm reading some OBJ file, in this case the bunny, and doing some mesh refinement on that, and then just visualizing that. So you can see on the left, I've split it out into reader, filtering, and rendering steps. And this gives you just a flavor of what a complete VTK visualization entails. So it's not much Python code to get you started using VTK. So Python bindings in VTK have made a lot of progress over the 20-some years that VTK has been around. So object creation just involves, it looks a lot like creating an object in C++. In VTK, there's a lot of instances where you want to set, say, one point, and it's convenient to define a point in some small double array with like 3 elements. So here, for instance, if there's a center of a sphere, you want to define that in x, y, z coordinate. On the Python side, you can either pass in an array or a tuple for these member functions in C++ instead of some double array. And you can also get, sometimes member functions in VTK return a pointer to an array. And in some cases, that's assumed to be just like a 3-element array. So if we get that center back, on the Python side, you get a tuple, XYZ components. For the VTK classes that have overloaded operators in C++, those are mapped to the same operator in Python. There's also support for return parameters. So in this case, we want to find the intersection of a line with a plane and where in the parameterized if the line is parameterized from 0 to 1, that where that intersection happens on the line is returned in this t variable. So in Python, we have basically the same code call, but with a special type, this VTK mutable type that supports the return parameter. Kind of pass by reference semantics here. Another really cool thing is that the help system in Python works with VTK. So for the wrapped VTK classes in Python, if you call help on any of them, you can get information about them. And this comes directly from the Doxygen documentation on the C++ side. So here I wanted to find out about the setRadius function in the sphere source, and I get the documentation back from that. All right, so VTK itself is organized on the C++ side into quite a few modules. And when you import VTK into Python, these all come in at once. So we haven't split it up into all the various modules on the C++ side. So the good news is all you need to do to use VTK in Python is just import VTK. There's a convenience executable provided with the VTK distributable called VTK Python, and that it has an environment set up to make it very easy to import VTK. You don't have to set up environment variables or Python paths or anything. So more recently, some recent work has gone into, 5 minutes, okay. Providing an interface between VTK data arrays that I talked about earlier and Numpy arrays to go back and forth between those two. So my code example here on the right shows how we can do that. So if imagine I've got some data file, STL, and somehow it has a pressure field associated with it. I can get that pressure field as a NumPy array using this NumPy support module in VTK, which converts it to a NumPy array, do my usual NumPy operations, And I can actually create a new array. Say for some reason I wanted to compute a normalized pressure array. I can do that and then add it back to my VTK object. And so a lot of this stems from the fact that VTK does a lot of things, but it might not do the thing that you want it to do. So there's some efforts in the past to create a special array calculator class that has its own syntax and has its own parser, but turned out to be slow and kind of limited in itself. So using this interface, we can get full power of Numpy with VTK. And it's very nice. There's also support. So one thing that doesn't provide is support for when VTK is run in parallel mode on distributed memory supercomputers. All right, so VTK supports distributed parallel algorithms, and Numpy is usually assumed to run on a single processor. So how do we provide some kind of Numpy interface or Numpy-like interface for data that's arranged this way? And the solution is to provide a Numpy-like interface that handles the distributed data. So this involves a couple of pieces, a wrapper for VTK data object and arrays, and a special algorithms module that handles all the parallel and distributed data. So in VTK, there's a Numpy interface package with a dataset adapter module that you can use to wrap your VTK objects. And what the wrapping provides is some Python object that provides an interface to, remember I was talking about the point data, and it's a dictionary interface, so it has keys. You can use the keys method to list all the arrays that are available, and use the dictionary interface to grab an array. And you'll see that in the middle, I'm checking to see, is it an instance of a Numpy array? And it is, so we can actually use Numpy on this array in all the usual ways, like the slicing examples I have below, and the other examples as well. But that doesn't handle the case of this distributed data. And so for that, there's the algorithms module. And this module kind of replicates a lot of what's in Numpy with most of the universal functions available, such as min and where. But it works across the distributed data in a parallel environment and gives you the right answer automatically, which is great. So you don't have to mess with MPI or anything like that to get your global minimum value, for instance. But also provide some additional functions that Numpy doesn't have. So your data set, you might want to find the gradient at various points, but sometimes you might have an unstructured grid or you might have a structured grid, and you want to find the volume of those cells. Well, nothing like that is available in Numpy, but this algorithms module provides that. So the bottom example, I can compute all the volumes of the cells in the data set and return that. And it's just a couple lines of code. I'm going to skip this. So just a couple of other random points about Python package integration of VTK. You can use this with PyQt bindings to create full-featured applications in Python and never touch the C++ side. And somewhat randomly, we want to render nice math expressions sometimes in annotations on your visualization. So we're actually using matplotlib when it's available to do that, and we just grab the vector data that comes from there and render that on the screen to provide annotations. And I'm going to try to run through this very quickly. So ParaView, this second part of my talk, is based on VTK, and it provides kind of a nice friendly user interface to VTK functions. Now, it started as a GUI for exposing VTK and its particular its parallel capabilities. And it really is tailored to run on a client-server mode, where the client's running on your laptop and the server is running on some parallel computing resource. So since the beginning days, it's grown into a suite of parallel visualization applications listed here that do various things. But Python's integrated a number of ways. There's a Python console that you can use to control the visualization in ParaView. So think of this as using matplotlib from a regular Python console, but it's controlling things in ParaView. You can, as I think I mentioned, you can record traces of what you've done in the form of Python scripts that you can replay later. So for example, if you want to convert a bunch of data files from one format to another, and ParaView supports those data files, you can trace the opening of the file and then saving it as a different format, and then use that as a basis for a script that will do that 1,000 times. There's also a Programmable Filter, which is a very powerful tool where you define a Python script where you can create either new data arrays or entirely new topology in your mesh, for instance. And that also provides access to this Numpy dataset adapter that I talked about earlier. Some other filters include a Python calculator where you can have simple one-liner expressions to compute some new value, some new arrays associated with your data set. You can use Python to create annotations. So this is where you could do your LaTeX rendering, as well as display statistics about your data set, such as the minimum or maximum values. And then lastly, there's the Python view, which is a way where you can provide a Python script that produces a VTK image data object that will then be rendered alongside the other visualizations in your ParaView session. So here you see a matplotlib rendering of a couple of graphs alongside the 3D interactive window in ParaView. And lastly, just talk about there's ParaView Web, which is based on PV Python, which is a Python console for ParaView. And this is a web front end, basically, that replicates most of what's in the, or a lot of what's in the ParaView client on the desktop. So, future work, we're working towards supporting Python 3, and that should be coming sometime next year. And thank you for your time.